Thanks, guys. Friday afternoon, I know it's hard, so thank you for being here, and I hope I'll be energetic enough to have you be excited as I am on this stuff. So let's get started. IoT malware. So I've heard that about the IoT talk that was earlier today, and I was told that it was very radio-oriented. So this is not going to be a repeat of that talk. This is going to be really different because for me, IoT is kind of a different subset and has different characteristics, which I will outline later. But so this IoT stuff is very trendy, and this is what we're going to talk about today, and started to be in the global news because of Brian Krebs talking about it in 2016. And what happened really behind that is the OVH 1.5 terabyte per second DDoS attack that happened last year. 1.5 terabits attack on a provider this big affected them. I mean, it's a lot of data. And what was fun, this is OVH's CTO. He published like raw logs, those line like grepping logs and then piping into Hawk and then doing some statistics. So, really technical details about that attack. It's not just like, someone saying like a DDoS protection vendor saying, oh, we received this XYZ attack. I actually believe more a screenshot like that. And then he went further. He said like, this was 145,000 unique IPs coming from most likely cameras, DVR, each with a connection between 1 megabit per second and 30. So this together built up to 1.5 terabit. This is the tweet that is behind that statistic. And so for me, it was like, okay, I mean, this is really a problem. I had been looking into that problem before, but for me, it was more novel and interesting and doing reverse engineering on something else than Windows, which is refreshing. And so I have been talking about it, but this is where really it became important in my eyes. Like, okay, it's bad malware, it's basic malware in the cases that I will outline today, but it's getting important and the problem will have to be fixed. Otherwise, the pipe will be clogged by this stuff. The internet radiation background noise is no longer just noise. It's affecting, our internet lives. Oh, yeah, I speak in the mic, but I might. All right. So yeah, this is why I've been talking about it, studying this since 2014, and since then I kind of shifted our approach and wanted to really understand what was going on. This is the lessons learned throughout, and this is our agenda. So we'll cover the problem area, which is collecting threats. This is very different and why it's different. We'll go through Honeypots, which is the solution outlined at the previous section. Then once we have samples, we'll go through the reverse engineering challenges that are specific to IoT malware. And then the data analysis and the ongoing tracking that you need to do in order to track larger operations. Then we'll talk about 3 cases of specific malware that I've analyzed in the past few years, some of which are really recent as this summer. And then we'll talk about the future, like what should developers do to fix this, and some takeaways. But first, I wanted to say it's cool for me to be here. It's my birthday today, so I'm here at COUNTERMEASURE talking about what I love. It's a coincidence, but still, I'm glad to be here and exchange with you guys. And for me, I'm not leaving until 6:30, so back to Montreal, so I'll have time for a few drinks and celebrate my own birthday. So who am I to be talking about that? I'm a cybersecurity researcher working at GoSecure, where I lead the research team. And the cool thing is I pretty much have the mandate I want, right? I do research. The CEO just tell me cool things that you can talk about and, raise the bar of the security community in Canada. As long as you share it and everyone can benefit, I'm down with that, which is pretty cool. I'm also a co-founder of MontreHack, so these are workshops that we do every month. It will be our 5th year in February, so I've been doing that, focused around solving CTF challenges, capture the flag challenges. I'm also the vice president of the training sessions at NordSec. If you don't know about NordSec, look it up. It's a conference in Montreal in May. It's a really cool place to be. A lot of professionals, and it's quite a technical conference. And this is our hardware badge that we have. This is 2 years ago but it's a fun conference, and I would be open to talk about it. I've spoke at many places before, so I'm used to this, but just some kind of bragging rights. I spoke at Black Hat Europe, Black Hat USA Arsenal this summer, Virus Bulletin, BotConf, DerbyCon, DEFCON, places like that. I really enjoyed sharing and this communication act that we can have together. But I'm also kind of fond of the technical stuff. Being at all those conferences, you see a lot of conferences. I try to find my niche with like speed and technical content. I hope you'll like the style. Maybe not. So problem area. Okay, IoT. I said I was gonna redefine it, not to avoid, you know, saying things that are contradictory to this morning's presentation. So in this scope, or the way I see things, IoT is an embedded system. And so I was using embedded system malware before, and I had to switch to IoT because everyone's about IoT, and you get accepted easily when you pitch a talk proposal if it has IoT in the title. So an embedded system, what is it? It's a small CPU, small memory, not a lot of memory, and low cost. So it's really important to understand the constraint around the manufacturing and what the vendors have to deal with. It is usually networked. If it's not networked, I'm not that interested into it because it cannot be part of a bigger problem, you know? So Bluetooth, Wi-Fi, Ethernet, generally running Linux because if you write malware that targets Linux and you statically link your C library in the malware, it will run on anything Linux. Like it's a very, very compatible ABI, application binary interface, that Linux has been maintaining since like the first release of Linux. So it will run everywhere. And it has no user interface. No user interface is kind of important, and I'll have dedicated slides to it later. Where IoT is getting really problematic, and through my analysis and experience, is when you expose Telnet or SSH. This is where the things become parts of botnet, and this is an unnecessary attack surface. So this gets worse when you have that. Also, if you expose a full user land busybox, so a shell environment that is rich and non-custom, so I would say like a Juniper or Cisco command line is not a generic, you know, you cannot do small snippets of code or looping, or you can do TCL, I believe, on Cisco switches. But the fact to have a non-custom, a generic shell that can be so you can be attacked as if you are a Linux server or whatever the environment. This gets more problematic and more chances of being part of a botnet. If you have global default credentials, so admin to get in, this is a bigger problem yet because they will do some limited brute forcing of usernames and passwords, the malware I'm going to talk to you about. But if you would have a generated a password which is different on every device, even if it's printed on it, the problem would be really less global and problematic. If your device can be directly plugged on the internet, people will do it. They will expose it online, plug it not in the correct fashion. And so this is another case where things are getting more problematic. And if it can be mistakenly plugged, like WAN port or LAN port, you don't really know, it's dark, you plugged in under, you know, some table, you didn't look, you will see more of that exposed if you can make that mistake. Also, if it has benefits of being plugged on the internet, and this is where OVH's comment is related, DVR, IP cameras. This is the kind of stuff that you want to expose on the internet because you want to manage the show that you're recording from work, or you want to monitor your system remotely when you're traveling. And so this is, again, you know, making the problem worse. So the no user interface. Usually you'll see a web interface on, let's say, routers, home routers, mobile interface for some specific devices like a camera or something like that, or no interface at all. So just buttons and blinking stuff like a NAS, for example. But this is not enough because you cannot really investigate malware incident without a user interface, right? Malware is this complex thing. It's a piece of code which executed. So if you have only access to a web interface, you cannot list the processes running. You cannot see, is there a rogue process that you shouldn't run normally? So this is the problem of a specific to this field or this new type of devices. You have no third-party software on it also, which means you cannot have endpoint security. I know AV is not as cool as it used to be. A lot of people like to bash AV. Maybe less here, but when you're at a conference like Hackfest, they're like, yeah, boo, AV, they should die. You know, or a pen tester conference is all against AV or how they bypass AV. But still, AV is the way malware researchers are fighting and winning this war right now. AV is a collection mechanism. They have data, they have stuff, they have everything. Every time Cisco Talos publishes about something, they collected it somehow, and it's through AV or Honeypots, right? So it's very important part of the Windows malware fighting world. And so you don't have that on embedded system, and I'm not saying you should. This is an important caveat, but it is a realization. It is part of the problematic. So because of those characteristics, malware investigation on IoT is different than traditional desktop, mobile, or server-side threats. Desktop and mobile, you bring the bad stuff in, you click on links, you know, so it's the opposite for IoT, where the stuff comes inside your device. The problem of no UI, you cannot really reach the samples, or if you do, you run at the same privilege level of malware, which is a problem. As a consequence of that, and as a consequence of those characteristics, you will see also IoT malware infecting servers, but server malware infecting IoT doesn't really happen because of the low cost, which implies different CPU architectures than Intel. Low cost or low or energy requirements will make this piece different. So having the first problem, biggest problem, having access to binary samples. Since you don't run endpoint security, you cannot collect the samples proactively in that fashion. And since you have no UI, you have kind of a problem of trying to have access to those malware samples. So what are the different ways we could look at it and try to collect samples? First, you can solder on the UART port and have a console connection, and then have a kind of a management interface, low level. When you do that on most common routers, you get a root shell, so you don't have privilege problems and stuff like that. But it requires the actual hardware, and it doesn't scale, right? If I would be soldering every device I'm trying to do and collect samples and malware analysis on, I would still be in my basement doing some soldering. So it doesn't requires hardware and doesn't scale. That's what I was saying. And additionally, it won't work well on hardened devices. So if you want to catch ATM malware, for example, embedded, assuming it's not a Windows CE, but it's embedded Linux, this stuff is made to be resistant to hardware tampering. So it's probably all dipped in epoxy, and you won't be able to plug in your UART stuff on it. You can ask nicely for files to people, and I tried that. At the end of my slide deck, I have my email address, PGP key, and you can send me samples to my email. But again, it's kind of pushing the problem away, right? Because it's still going to go back to this for the person trying to give you samples. So this is something I've tried to do, I've been doing for a few years, and it happened for me once that I got a file and by email of a MIPS router, but it doesn't scale again, once in 3 years. You can also try to find a way in. So since most malware gets in via Telnet or SSH, and there is default creds, you can reuse that path and scan the internet, connect, and then list file, list processes, and collect stuff. Of course, you see where I'm heading with this. First, it could be tampered. It happens at the same privilege level as you, so you could be inside of a fake Telnet daemon where everything is hidden away. And we've started seeing stuff like that with OpenSSH malware. The Iberi group, they're now doing that. So if you're connecting through SSH to a server and you list files, the Iberi artifacts will be hidden from you. You need a console access in order to realize that you're infected. So it can be tampered with, and it is on server-side, sophisticated server-side malware. But the biggest problem is it's illegal, right? I cannot scan the internet, punch in default creds, and start collecting stuff, or at least I wouldn't say it publicly. No, I'm not doing it. I'm not doing it. I promise. So it's not a good way to operate. And you can do some hunting on VirusTotal, so put up some Yara rules, try to find binaries of various architectures. But there is it's like always the same stuff that is just recompiled, and there's a lot of noise, a lot of uninteresting samples. And you don't collect the IOCs also, so you don't know whose IP is attacking. You just have the file. And nowadays, like the command and control server are put in on the command line for certain malware. So if you just have the file, you don't know where the CNC are, which makes tracking more complicated. And basically, it's just not a lot of samples. So the solution that we've designed at work is collecting threats by mimicking actual targets via honeypots. So we run honeypots and we mimic hardware, and we want connections and binary drop. The problem is honeypots are complex and are like high maintenance things, right? So a honeypot, basically, for those that don't know, you're trying to lure attackers into showing you their tools, techniques, and procedures, TTPs, tactics and procedures. Now you deploying a honeypot, there is a lot of stuff. The HoneyNet project is doing a great job at it. You need to pick a component architecture and design the way you want to do it. So here's what we decided, or what we faced as first choices for IoT specifically. Should we do the full thing in hardware or software? So of course it was not a complex decision. Software is kind of cheaper, and I wanted to do some geographic, see if trends were different geographically. For Windows malware, it's very clear. Like Brazil has a very different ecosystem than the rest of the world, for example. So I wanted to see if the same thing was happening for IoT. I can tell you, no, it's not. It's the same. But I deployed servers in Russia, in China, in Brazil. So I needed to go software route, right? So there are various types of honeypots: low interaction, high interaction. High interaction, you need to watch it closely, because whenever it gets infected, it's a full system, so it will attack other people right away, and you can get into trouble or abuse letters for it. So you cannot go at a conference for 2 days thinking, everything's gonna be fine, you'll have this dog and fire type image, mental image. So because of that, we went the low interaction honeypot route. So low interaction is kind of the matrix, showing the bad guys the best mimic of the environment that you expect, but not the actual real thing. So nothing really happens, but you collected the recon script and the files, and then you can, with the files, move on to reverse engineering, and has less of a chance of becoming part of the problem. So we actually deployed a low interaction honeypot, but added a little like botnet tracking component to it. And this is what I'm going to show you in a second. So this is the architecture we use for LinuxMoose tracking. On the left-hand side, you see that we actually ran a full ARM architecture, a QEMU VM inside a cloud provider, on which we deployed Debian Zorel's ARM images, so a basic Debian, and we detonated, as the CSIRC learned me to say, a LinuxMoose sample in it. So we had a real infected system. In front of it, we added a man-in-the-middle proxy tool. So this is a HTTPS interception tool. It will create certificate errors for sure. That it's the reality of doing such an attack. But the botnet guys, they just probably have seen so many that the way they automated things is ignore SSL errors. So this works in the field, I guarantee you. On the right-hand side, we deployed, so we hidden away the SSH and Telnet interface of our QEMU system. And instead, we deployed a Karif system. Karif is a low interaction honeypot I'm going to describe to you in a few slides. With a Telnet service, BusyBox environment, so the real problematic. It was based on an Action Tech router, actually. And router user LAN, full file system emulation, like copying the characteristics of the file system. We redirected the traffic to the proper components using IP tables. And we did in front of that full packet capture. So I have everything of months long of running these honeypots. The components I've pretty much covered them all. I think I'll just skip this one. We went with Karif as a honeypot because you can easily emulate the file system of a target device. It's written in Python. It's using the Twisted framework, so it's okay. It scales well. Twisted is complicated to understand, callback mechanism and all that, but it's still Python, so it's not as tedious as if it would be an unsafer choice like C, C++. You can easily modify the output of commands. So if you have an actual router, you can run commands and make sure that the carry will output the same thing. It's easy to patch, being Python. But it didn't have any telnet support, and we knew that the sample we were after were telnet brute forcing only, no SSH. So we were a bit disappointed, and during Christmas vacation, there was no one at work, you know, no one to report to really. So I decided to implement telnet support to Kari. We sent the pull request last August, and it got accepted. So Kari's telnet support was written by us the implementation was started during Christmas time. It took quite longer than I thought. But because of that, when Mirai happened, everyone was tracking Mirai using Kari and telnet. So I was pretty proud of that moment, although I got no credit for it. Thanks. So man-in-the-middle proxy, as I told you, we used it, and we needed to intercept traffic that was out of a SOX proxy tunnel. So it was not your usual like pen test, you know, I do a layer 2 man-in-the-middle and then I unstrip everything. It was trickier, and I tried to use BetterCap to do so, but BetterCap really failed at me. It was crashing. It has no binary, no reliable log that I could parse in a machine way. You know, it was kind of a loose format text file, which is not good when you have like 20 gig of log and you need to extract like all of the unique IPs that went through this. And so for me, as a recommendation for malware hunters and people doing long-term SSL stripping, a man-in-the-middle proxy really works well. But you need to do the IP table stuff, especially when it's out of a SOX proxy. For full packet capture, I recommend dumbcap. I think it's more modern, but some people hate the pcap-ng format. So for those who hate it, don't use it, or at least specify on the command line that you want pcap and not pcap-ng. But it's cool. It does automatic rotation, and I strongly recommend doing automatic rotation, because if you're going to parse 200 gigabyte of pcaps, you really need this flexibility of spreading that out on multiple cores, because if you use Wireshark or T-Shark, it always needs to reconstruct the whole TCP sequence, and it does so by loading all of the file twice in memory to do the sequencing, matching, and stuff. So it's way better to split them in advance so you can spread out the analysis. Move your SSH to a non-standard port and filter it out, so that if you rsync your pcap files out of the server, the pcap will not grow because you have SSH traffic in it, meaning that, you know, there's just a snowball effect here. So this is like a lesson learned exactly that way. So now we've got files, we have data, we need to do some reverse engineering. The biggest problem with the IoT samples I've analyzed so far is when the binaries are statically linked and stripped. So what does that mean? Well, statically linked, it means that there are no imports, no library calls, so everything is in the binary sample down to the syscall level. So system calls is how a program will interact with the Linux operating system in that case. And so this is a bit different on Windows. That you're guaranteed to always have certain libraries, but on Linux, it's really the contract between kernel space and user space is syscalls. So everything is in the binary, which means the libc and all of that. It's a lot of code to look at. Disassembling, even if your architecture have it, even if you have it like ARM, it's just a big blob of structures and pointers and arithmetics in it. So it's really not easy to do. Stripped means that the debugging symbols were removed. It's not by default, I think they are, or no, by default it's stripped, but a lot of the badly done malware out there, especially the IoT one case I will show you later, they don't strip, so you have like the symbols and you can go quickly. Other than that, you're kind of stuck with going after logging, like if the malware logs anything. But so for certain cases, like LinuxMoose, there is simply no logging. So you're with a binary. Just to give you a sense of what it looks like, so in IDA, this is 33 lines out of 500 functions that are all unidentified except the entry point. And so, sorry, all of this needs to be analyzed if you're gonna, try to find what's the malware payload, what's it's doing, right? So it's not simple code to analyze. This is, for example, the printf family, okay, of calls. So snprintf, sprintf, and you realize that there is an internal function called vfprintf, which touches a lot of stuff. And so if we zoom out and see, and this is not lines of code, this is not assembly, it's only variables and other subfunctions that it touches, right, or that touches it. So this is the bigger, like, proximity view of all of the ecosystem around vfprintf internal. And the syscall behind a printf is puts. So it's a single syscall, which is really generic. And so you have this mega abstraction on top of it, which is really complex. So if we go deeper and look at the implementation, so at the assembly level of the call graph of this is the vfprintf internal function. So this is just this function, and there are subfunctions, and there are a lot of data members around. So you can spend like more than a day reversing a function like that to realize you're dealing with a fucking printf. And yeah, at some point you're just like tired and angry, and you're like, no, this is not working. The ecosystem, Linux-specific ecosystem, makes it worse for reversers. So what you have is you have different compilers, so different versions of GCC, different versions of the libc, calling convention, not changes to calling conventions, but little changes here and there in the way they order things, the way they do things, which means that there is no IDA flirt signatures for these things, right? IDA flirt is kind of a quick binary matching thing that will identify common functions like what would be in the libc. On Windows, it works really well, and this is why you do not have to reverse memset and stuff like that. And another problem is that there is not a single libc. You have uclibc, eglibc, glibc, muzzle. There is a various ecosystem of embedded C library, because glibc is too big for some of these systems. So what we did at the time is we tried to map the syscalls with an IDA Python script, because the syscalls are just an integer, so you need to map them back to what the meaning is. So I extracted the constant from the kernel source code, and I just created a script that would find all the syscalls and just add a comment besides it. But it was just too big. There was too much stuff to reverse engineer. So I spoke with my former colleague of mine, Marc Etienne, very smart guy. And he said, I think I have an idea that could work. So what is this better solution? You reproduce the environment of and this is all static analysis, not dynamic. Dynamic analysis has other problems that we'll cover later. You reproduce the environment. So you find the architecture, the libc, and the compiler version. Usually you can find that in strings. They are not stripping it yet. And you build that library with symbols under the same condition. So under these same version, you build it on a modern system. Some timestamp will change, but this you can easily put away. And you use bindiff to map the functions. So you have one library that is binary equivalent to the other one, because symbols are stored elsewhere in ELF libraries. And so you will have this binary match. And with a tool like bindiff, you can import the symbols from one side to the other side. And then focus on the malware code, right? Here's what it looks like. So this is, again, of our LinuxMoose sample. On the left-hand side, you had all of the name primary, all of the sub that are unidentified. And on the name secondary is what we compiled. And you have all of the functions named there. So getC, vfprintf internal, opendir, inet ntop, inet p2n4, So all useful stuff that you don't want to look at, you know, because it's all binary, doing changes to integers and just tedious to reverse engineer. And so with this approach, we compiled with uclibc 0.9.33, and it was they were using the OpenWRT toolchain to do the compiling. And so we even had in that part of the toolchain, the artifact of the compilation, we had the SVN revision number of OpenWRT. So I was able to do a SVN checkout of the exact revision that they used to compile. So with this, we mapped more than 225 functions with high confidence, high similarity, can import all of that. And then after we were reversing, you know, malware, code written by malware author, not the libc. Our life was better. So why I start with static analysis is because dynamic analysis is another headache. You have to emulate some hardware like storage, like NVRAM, and I know that they are really good, the guys who, you know, reverse engineer and try to find flaws into IoT and stuff like that. They all have tooling and they all are better equipped than I am, and I should look into solving these problems on my own. But for me, it just turned out to be more portable across different devices if I use the static analysis approach. So basically, this is what we've been doing. And right now, I want to say that there is no anti-debugging, no, you know, detection of a sandbox and stuff like that in that malware. But we know through evolution and through our classic arms race that we've been talking about for the last 2 days that it's going to happen. So we need to be prepared and proactive and ready for this when it will happen. So now we collected a lot of data, PCAPs, logs, for months, distributed, so Russia, Brazil, China, and you need to analyze all of it. I'm going to go through like really down technical details of what actual tools we were using. So we decided to put that on a single server because, you know, our laptop only have a 512 gig, and it was more than that. Well, not really, but, you know, I have VMs and stuff and pictures of my family. So we decided to pull that in all in a centralized server, and we decided to use IPython Notebook as kind of a collaborative IDE. So IPython Notebook is a web-hosted tool, and this is all open source, by the way. And so I could share code snippet with other engineers at work and or data scientists very easily, and you can just run it interactively, and it keeps running. So whenever you load a piece of code, you can, you know, close your laptop, leave, and not be afraid that because you did, you know, a mount of a remote file system, you will lose your computation. So for long-term computation, this works really well. We use the scalable libraries. So let's say you produce CSV files, which is really useful to, you know, you use PCAPs and then output through T-Shark, you output CSV files. Python's CSV is really flexible, but it's slow. With Panda, we did a more than 200x faster, you know, so for when you have several gigabytes of CSV, it matters. NumPy, SciPy. So Panda is kind of the Python's implementation of the R language, which is pretty powerful. R still has some advantages or some edges, but for the advanced statistics stuff that I don't even understand, so I didn't need that power. Then we parallelized everything that was heavy I/O or heavy CPU with GNU Parallel script. So GNU Parallel is amazing if you do computation. It's like Xarg, a drop-in replacement from Xargs, but it will detect the number of cores on your system and just maximizes the parallel tasks automatically, like no command line, like just if you run parallel instead of Xargs, it will maximize core usage by default. You can have it watch for memory outage and kill and restart processes. So to crunch, let's say, I don't know, 8,000 PCAPs and have the output stored in a safe way, because if it's concurrent and you put it all in the same log file, you could have concurrent writes, but GNU Parallel take care of that. It's a very amazing tool. Recommend it. Then specific tools for specific data, right? T-Shark for PCAPs. You explore with Wireshark, but once you found what you're looking for, T-Shark, dash capital T fields, and then dash E and the field names that you're interested in. man-in-the-middle proxy for man-in-the-middle proxy logs, kind of obvious. So this has been our tool chain. And in the future section, I'll tell you like why this looks medieval, and I understand, but I understand the need for dashboards. We'll get there eventually. But now it's the story time. So our famous 3 cases I want to talk to you about. First one is the Lizard Squad guy, which was known as GAFGit malware. And GAFGit is the industry's trying to censor the real string inside this malware, which is gay fag. So the industry just like, you know, flipped some letter because there was a kind of a gay fag string, and it would quit if you send it gay fag, something like that. This is the Lizard Squad moniker, if you want, their online face. Who are they? It's a black hat hacking group. They did a lot of DDoS, and they had a DDoS for hire service called Lizard Stressor. They are the ones behind the attack on the PlayStation Network and Xbox Live in Christmas 2014. And this was kind of really public, but it was not done enough for them to be arrested or to be going after. What happened is what made them really get law enforcement attention is when they started making bomb threats, but kind of weird bomb threats. Let me explain to you one of them. Is they called American Airlines or an airlines from America, and they said, oh, this guy, we have strong indication that he has a bomb in his luggage. So it kind of escalated really quickly, and they forced the plane down. But the guy who was the VP of Sony, in charge of the gaming branch of all of Sony, so a very important guy, and he got treated like a criminal. You know, the plane landed, and when a plane lands because of you, you have to pay for the fees of landing a plane in emergency. I think some BlackBerry guys have a story about that. I'm glad to have a laugh. So what happened is this really got them some attention, and several of them were arrested in 2016, I think around August or September timeframe. But still, the malware is like, again, it's the thing that hit the most the honeypot still today because the source code was leaked. And various variants were made, and it's really easy to compile, and the tool chain is easy. But still, I mean, this description of a cyber group is not like cyber criminals or you know, bad actors or targeted attackers. It's more like cyber rascals, right? Like come on, guys, you should know better, grow older, and stop doing that kind of reaction to it, you know. But so Brian Krebs confirmed that a Lizard Stressor was running on hacked home routers, so we knew that even though they could infect server, they are also targeting routers and IoT. The malware itself, GAFGit, Powbot, Adra, Katan, all of these are the same code base that was forked and has different features depending on who wrote it and what subgroup of Lizard Squad is using it. There is a telnet scanner. They support several types of flooding mechanism, supports multiple architecture, like Super H, which, I mean, I'm not even sure they infected one thing, Super H. I know nothing that runs Super H except the chip in the camcorders, which don't have a telnet exposed. So I just don't understand what's going on here. But, you know, GCC compiles to it. So I think this is what the reason is just like, oh, we can support it, we'll do it. MIPS, ARM, x86, PowerPC. It's fun to have an x86 variant because you can reverse it comfortably with all of your tooling, you know, with x86, the decompiler and all that good stuff. So thank you, Lizard Squad, for providing one. The server code even acknowledged that they were supporting or targeting IoT now. So this is one of the versions that I had source code access to. And you see like, oh, now with refrigerator support. The attack vectors that they're using, they're really opportunistic. So they used shell shock when it was cool. But otherwise, it's credential, brute force, SSH, and telnet, with a short list of weak username and passwords. Shell shock looks like this. So they trigger the bug, the famous shell shock signature. And then they wget a script, and then they launch it in a shell. And that script, what it does is it downloads every variance. So all of the architecture that are supported, shmod it to make it executable, try to run every architecture, and one of them will run, hopefully, and that's it. This is their fancy payload. We've seen variants with HTTPS support and also one with Cloudflare protection bypass, which was interesting. All hand-coded in C. So Cloudflare protection is based on a JavaScript challenge that your browser solves, so you don't even see it. But you have this kind of, you need a full JavaScript interpreter. So what they did is they reverse engineered the JavaScript challenge, and they implemented just what they needed in C. They implemented just what they needed in C to be able to solve that challenge. So this is kind of interesting and kind of probably a group to track more closely different tactics and better implementation, right? But it was still a lizard stressor code base. So are they sophisticated? Not really. Database was leaked, passwords in plain text, you know, a lot of you know, bad OPSEC. It's an IRC botnet, so you can log on the IRC command and control. You can see the number of users. You cannot list them, but you can see the global server stats. So you knew, okay, this sample has this amount of bots. You see the nickname of the bot masters. So it's pretty like, you know, the YOLO operation, if I want to say like the cool kids. Mostly gamers-related targets, so DSL lines, game hosting companies, stuff like that, really around gaming. So even though some were arrested because the source code was leaked, it's still very prevalent, but it's operated by numerous unrelated actors, we think, and still focused, the malware very focused on DDoS activities. So the second story is, how am I doing on time? Have like 15 left, or?
5 minutes to question.
Oh, can I bust like the guy before me? Because it's coffee break after. Okay, I'll see what I can do in 5 minutes. So LinuxMoose was a botnet that was selling fraudulent followers on Instagram. Okay, we tracked this for a long time, but and this is what happened. I first started tracking it when I was working for ESET, but since then, with them we partnered, and I continued the operation more on the social network side of things. So this is what we built in order to catch the thing, and you saw the component, but this is more of a dynamic view. We added in front of it the man-in-the-middle proxy attack, and this is how we got the traffic. So we published an extensive paper about it, and we spoke at Black Hat Europe last year on it. And this is, in a nutshell, in one slide, our findings. I don't have the time to go through it because I have a lot of stuff to cover still. But it's a very interesting, very unique, and money-making machine. But no one is interested. Law enforcement is not interested because there's not really victims here. So chaos is the thing we did this summer. SSH credential brute forcing with some recon script that is interesting. One of the components is a raw socket backdoor for various reasons. It's kind of novel and interesting. I like doing that. I'm about to publish a blog post about it. It does bozo cryptography in order to obfuscate, so you cannot, if you have a Wireshark dump or PCAP, you cannot see exactly what's going on. It uses hash max, so there is integrity and replay attack prevention. So they kind of show some sophistication. Is it good? No. If you saw the initial handshake, you can decrypt the whole traffic, but it's still something that would require some work, right? Blog post, I say early next week, but I've been saying that for the last 3 times I did that presentation, so maybe not next week. But the thing is, I need to scan the internet to find an amount of victims, and my scanning the internet thing it's not as easy as I thought it was, so I'm almost done. So future work, I want to able to collect the stage 2 samples because the bad guys, they started using droppers now. I want to emulate more devices and make our honeypots harder to fingerprint because it's the classic arms race that is happening right now. Data analysis, I'll just say one thing. Elasticsearch, Logstash, Kibana. I will deploy a ElkStat dashboard and I will show that to management and I will continue to get money for cloud honeypots, right? I would like to build IDA-float signatures, a build farm to cover all of these architectures, ideally. Now, fixing the problem. Device vendors should stop using default credentials and use per device credentials instead. They're already doing it for the wireless interface, you know, SSID and password, so they can do it. Don't say they can't do it, they can do it. They just need to do it. Stop exposing general purpose management port, and if you have to do it, put a button and put a timeout. So you need SSH access to your router or your IoT. You need to push a physical button, then for 5 minutes you have physical access. I understand this is for consumer devices. I don't want network admins to panic or attack me. It's not realistic in that context, but admin is rarely there. Consumers should put password on the devices, and I even advise people whenever they are at another, like you're visiting a friend and you use their Wi-Fi, go hit the 192.168.1.1, and if you try admin or admin Linksys and you get in, change the password. Just change it for them, and then write it down, and then put the paper on top of the thing, right? I have a demo. Admin, your new password, and don't use your new pass, because attackers will add it to the list. And then, this is the IP. Thank you. Good deed. So for developers, you need to have, and I'll just go really quickly to that, but you need to have a hacker mindset when developing features. So attack scalability, and this is like a DDoS amplification attack are real. So anytime you develop a feature, think like, okay, this one devices, I think it's okay, but if there is 100,000 and I still abuse or use the same feature, does the hacker have an upper hand in that context or not? You need to think about that. And you need to leverage the implied physical access. For consumer devices, you have physical access. For anything that is sensitive, you should require some physical interactions. So the takeaway is IoT is insecure, but it can be fixed for the low-hanging fruit problems. And then I'll try to be in advance and tackle the next generations of problems. And we'll be ready to have the samples collected. And then we'll talk about what's the next generation of fixes required. But for now, 99.9% of the stuff I saw, just the simple advice I said earlier would get rid of that problem. I understand some visionary talk about IoT in like complex terms, and they have like more thoughtful advice than me. But I mean, I'm just focused on doing a Pareto principle here and aiming to fix 80% of the problem with really low effort. And this is my advice, my takeaway for today. So with this, thank you so much for your time. Sorry I went through. I went over time, but I want to say thanks to the Countermeasure staff and volunteers for the speaking opportunity. And I attended many talks, and I really enjoyed Countermeasure. So for me, it's a great event. Thank you.